Good morning and afternoon, everyone. This is Sean from eMemory. It's our pleasure to join the wonderful event and share our experience about embedded non-volatile memory adopting in HPC, AI, and security applications. Here's today's title: Secure OTP and Function IP for HPC and AI applications. First of all, I'd like to introduce some facts about eMemory. We are founded in the year of 2000, and we are the largest pure-play embedded non-volatile memory IP developer in the world. We have around 260 members, and over 70% are technical-related developers. Along with past 21 years hard work, we have issued over 940 patents in the world and has a very strong relationship with worldwide foundries like global foundries. We co-work with over 2,000 fabless design houses and have over 5,000 NTO records. For each quarter, there are 1.5 million wafers shipped out with eMemory IP inside, and the accumulated amount reaches 37 million wafers. eMemory worked with partners on advanced nodes, including FinFET and SOI process to support reliable secure OTP and security-related solutions for AI and HPC markets. Solutions on 22 FBX are already fully qualified, and we are going to move forward to 12nm families in the near future. Embedded non-volatile memory play crucial roles in advanced system-on-chip products, include analog trimming, function selection and repair, parameter setting, and secure storage. These advanced system-on-chips are equipped with 5G communication, high-speed computing, machine learning function, and also sensing capability to fit in data center, cloud computing, aerospace and defense, smartphone, VR, AR, digital currency applications. Here is the analog trimming and function selection scenario. First is the analog trimming. The variations of standard devices will impact the overall system-on-chip performance, especially in the advanced nodes with very sensitive process window. Design houses will add trimming flow along with wafer sorting procedure to improve yield and also chip performance. And this trimming data has to be stored carefully in a dedicated memory array. A secure and reliable NeoFuse OTP is the best candidate to meet this job. NeoFuse has no reading cycle limitation. Its high performance reliability and low power operation features can keep this important data safe and ready to use at chip power on stage. Another basic feature is function selection. Like chiplets used in data centers, the interface and communication protocols revised regularly, and the system operators are forced to keep upgrading the firmware and hardware setting. Therefore, adopting embedded OTP in a chiplet is the most cost-effective design in the chip architecture to minimize the chip replacement cost and also increase maintenance efficiency. Besides analog trimming and function selection, hardware security is a rising concern in the SoC market. Let's use the PSA information from ARM to explain the security architectures and functions in a SoC. In these security functions, secure storage is directly related to embedded non-volatile memory. and other functions like the anti-rollback, secure update, secure boot, attestation, and the unique ID. All of these are related with embedding the multi-memory for some different levels. There are several different methods to do the data storage. The most left method is a separated SPI flash. This method is very cost-effective and reliable, but the large footprint is not very good to modern equipment. Besides, the control interface is a standard format. That means the data stored in a SPI flash may be extracted easily from the hacker. The middle left one is an embedded flash. It is small and safe compared to SPI flash, but this approach is limited by technology node. Besides, the data is stored in a floating gate via electrons. That means the device do not have enough resistance to high temperature baking, UV or gamma ray exposure. The middle right method, eFuse, is a common solution in advanced node. It is widely provided in most foundries and easy to use. But eFuse suffers some obvious disadvantages along with its natural mechanism. Because eFuse is programmed via EM phenomena, there will be some natural recycling limitation with this technology. Besides, the programmed cell is easily to be spotted by a simple optical microscope. That means this method is not safe and reliable enough for some critical markets. The most right method is a patented Secure OTP structure from eMemory. The cell is operated with quantum tunneling effect. It's a very small footprint, high reliable, red hard, non-visible feature, and can be migrated along with technologies. This is the best method to meet the low power operation, high reliability, and secure requirement for advanced SoC applications. Let's go deeper with NeoFuse Secure OTP cell structure. The program mechanism of NeoFuse is using quantum tunneling path creation. We apply a controlled electric field between gate and substrate to create a non-visible tunneling path. This method can be applied on both traditional planar CMOS and also advanced FinFET process. The tunneling path is constructed with several dangling bonds. It is extremely small to be real observed, very stable at high temperature, and can sustain gamma ray exposure. Here is an example of TEM and SEM observation of quantum tunneling in NeoFuse. Compared to non-secure eFuse technology, NeoFuse is not visible through this high-resolution electron microscope. That means the inherent secure level of NeoFuse is the best candidate to security applications. In this page, some high temperature retention and operational time and also gamma ray exposure result of the eFuse OTP for your reference. The Secure OTP NeoFuse can sustain all of these extreme severe challenges and maintain very good reliable performance. Let's discuss more about the security threat for advanced SoC. If we look into the detail of PSA standard, the most important part of the security function is all developed based on the UID in the SoC. UID is the soul of hardware root of trust, and the root of trust can be extended to secure storage, authentication, and anti-counterfeit functions. The security of the SoC can be divided into software-based and also hardware-based. Software-based protection is cost-effective and easy to be implemented and updated. But the question is, the software-based protection is only as strong as the operating system's security level. We can see that the non-invasive attacks takes over 97% for all of the security threats. That means the software protection may not be the good enough solution to protect the valuable SoC for HPC and AI applications. Comparing to the software-based protection, hardware-based root of trust is getting more attention recently, and that's including the physical unclonable function. PUF is a physical derived fingerprint that serves as a unique ID for a semiconductor device. Our PUF is derived from the unique and random physical characters created during the manufacturing stage of the chip. These physical variations are unpredictable and unclonable, all of which make the NeoPUF and PUF-based solution ideal as a root of trust for security functions for semiconductor devices. The quantum tunneling-based NeoPUF is originated from NeoFuse technology and share the same fundamental cell design and operating schemes. That means NeoPUF has the same high reliability and security performance as NeoFuse. And we can easily to combine NeoFuse and NeoPUF together to provide both the inborn random bit strings and also the programmed area for the important data. NeoPUF is a true ideal PUF, and it improves reliability and randomness from the old style SRAM PUF. Because of the excellent retention and randomness performance, ECC and hash, its functions is not necessary to be implemented. It is considered as the most important and reliable root of trust and can execute true secure boot procedure with instant ready features. NeoPUF can 100% replace the traditional risky key provision from outside HSM flow. In the past time, chip or system provider have to create the UID or secret numbers through an outside HSM and program the bit string into the chip. There are several weak points of the flow. First, insider and software leak. The random number generator algorithm in the HSM is controlled by operator. Insider and the weak point of the algorithm are always the concerned point of security protection. Second, the chipmaker has to design a complex protection for the program path. Third, the test port is always another concern point. Because you have to program data inside, there must be some testing port like a JDAG. So the designer has to pay attention for the test port protection. Comparing to the traditional risky HSM program flow, NeoPUF can build up a man-free hardware root of trust with a solid security boundary, and exclude all of the possible weak points from the traditional method. SoC hardware security is becoming a must criteria in modern applications, especially for HPC and the AI field. And PUF-based hardware root of trust is the most important and fundamental factor. SoC giant like Intel, AMD, They already include hardware root of trust as a core structure for chip security applications. And ARM also implement hardware root of trust into their V9 series. The chain of trust for HPC and model data protection for AI are getting more and more attention. That means the hardware root of trust is getting more attention for these applications. Usually, the hardware root of trust will be equipped with other functions like NeoFuse OTP, TRNG, crypto engines, hash and MAC algorithm to achieve data encryption, cloud authentication, identification, and other security functions. Even these functions can be achieved by software approaches. But as we explained before, a hardware-based total solution can provide the best and comprehensive protection to the valuable chips and systems. Besides Secure OTP and PUF, eMemory also provides comprehensive all-in-one solutions of the security protection to our customers. There are three different products. First one is PUFRT, PUFIoT, and also PUFSE. For the PUFRT, we combine Secure OTP, TRNG, and PUF together to provide the root of trust solution. For PUFIoT, it is combined with PUFRT and also of the crypto engines to meet the IoT applications. And the PUFsE is the PUFIoT combined with embedded flash controller and other security core functions. That is the most comprehensive solutions for the SoC applications. In summary, secure embedded non-volatile memory NeoFuse plays some critical roles in advanced SoCs. That includes low power operation, high reliability, and security. Its main three characters construct for the Secure OTP NeoFuse. NeoFuse derived NeoPUF can build up a strong hardware root of trust and provide the best hardware-based protection for HPC and AI applications. Thank you for your listening. Please contact us if you have any question and comment.